In this research, the authors investigate the dynamics of a partially driven recurrent neural network (RNN) model, focusing on how the proportion of neurons receiving inputs and the strength of input signals affect the network's behavior. The model is defined by two types of neurons: those that receive inputs, X, and those that do not, Y. The authors derive the maximum conditional Lyapunov exponent, MCLE, to understand the stability and chaos in the network. The network's behavior is influenced by several parameters, including the input partiality, P, the sparseness of recurrent connections, alpha, and the recurrent coupling strength, G. The authors show that for sufficiently large P, the MCLE decreases monotonically with the input strength, indicating the suppression of chaos. However, if P is smaller than a critical threshold, PC, even significantly amplified inputs cannot suppress spontaneous chaotic dynamics. The study also reveals that the value of PC is intrinsically determined solely by the strength of spontaneous chaos in the RNN. This implies that if P is above PC, it is possible to bring the neural network to the edge of chaos, thereby maximizing its information processing capacity by amplifying inputs. The mean field theory is used to analyze the statistical properties of Xi, T, and Yi, T, which are assumed to follow Gaussian distributions. The authors' findings suggest that the input partiality plays a crucial role in controlling the network's dynamics and computational performance. The paper discusses the maximum conditional Lyapunov exponent, MCLE, in a recurrent neural network, RNN, with sparse connectivity and input partiality. The authors derive an analytical expression for the MCLE, lambda, as a function of input partiality, P, and input intensity, sigma. They also introduce a scaling parameter, Xi, to amplify input signals and calculate the MCLE conditioned by infinitely large inputs, lambda infinity. The authors first derive the evolution equation for the variance of the input, k, t, and then use this equation to obtain the MCLE, lambda. The MCLE is found to decrease monotonically with increasing input intensity, sigma. However, the MCLE remains positive for p equals 0.4, while it falls below 0 for p equals 0.6. This indicates that amplified input signals can suppress chaotic activity in the RNN when p greater than 0.4. To further understand the relationship between input partiality and chaotic activity, the authors calculate the critical input partiality, P_C, at which lambda infinity equals 0. They find that P_C depends on the recurrent weight intensity, G, and the sparsity, alpha. The critical input partiality increases with decreasing G and alpha, indicating that chaotic activity is more likely to be suppressed when the network has weaker recurrent connections or sparser connectivity. The paper also presents numerical simulations to validate the analytical results. The simulations confirm the monotonic decrease of lambda with sigma and the existence of a critical input partiality, P_C. The authors conclude that their analytical approach provides a useful framework for understanding how input partiality affects chaotic activity in RNNs with sparse connectivity. In this research, the authors investigate the dynamics of a partially driven reservoir neural network, RNN, and its application to reservoir computing. They introduce a critical input partiality, PC, which determines whether chaotic activity in the RNN can be suppressed by input signals. The authors derive an analytical expression for PC, showing that it depends on the strength of spontaneous chaos, quantified by the maximum Lyapunov exponent lambda 0, and is independent of the sparsity of recurrent connections. The authors then examine the information processing capability of a partial input RNN employed as a reservoir for reservoir computing. They evaluate the memory capacity, a measure of the ability of a reservoir to perform short-term memory tasks, and its relation to the maximum conditional Lyapunov exponent, MCLE, lambda. The results show that the memory capacity is maximized near the critical value of MCLE, lambda equals 0, corresponding to the edge of chaos. The authors also discuss the implications of their findings for reservoir computing. They suggest that by tuning the magnitude of input signals, a partial input RNN can be constructed at the edge of chaos, where optimal computational capability can be realized. This approach provides a novel way to design reservoir computing systems. Furthermore, the authors discuss the limitations and assumptions of their theory, including the existence of a critical input partiality in other types of RNNs and the conditions required for the existence of the maximum Lyapunov exponent. They also highlight the distinction between the sign of the MCLE and the echo state property, ESP, noting that a negative MCLE does not necessarily guarantee a specially. Overall, this research provides a comprehensive understanding of the dynamics of partially driven RNNs and their application to reservoir computing. The authors' findings have important implications for the design and optimization of reservoir computing systems, and their approach provides a promising direction for future research in this field. The pages discuss the concept of chaos and its role in neural networks, particularly in the context of recurrent neural networks. They highlight the importance of the edge of chaos, where the network's dynamics are complex but still predictable, allowing for optimal information processing and memory. The papers cited explore various aspects of chaos in neural networks, including the suppression of chaos by noise, the role of critical dynamics in brain activity, and the impact of synaptic weight distributions on network behavior. They also touch on the concept of optimal sequence memory and the generation of coherent patterns from chaotic networks. The discussion is dense with technical terms and mathematical concepts, such as Lyapunov exponents, edge of instability, and second type of criticality. The authors emphasize the significance of these concepts for understanding neural information processing and the potential applications in fields like neuroscience and artificial intelligence.